लिंक में शेयर करो। ले बना के ग्रुप में भेज। भेज भेज। यूट्यूब पे प्ले भी करके देखना। ये चल रही है इसमें स्ट्रीमिंग। तो कोशिश में रखवा है कि मैं क्या बोलता हूँ। एक चार का तो हमको पता है। एचपी वाला ठीक है बैठा होगा। स्क्रीन चालू हो गई। चाय पियोगे नाश्ता करोगे या हर चीज से बोलते हैं। हर चीज चाय। सर एक सेशन क्या है। शिट पढ़ना होगा लिखने वाला सर रजिस्ट्रेशन मटेरियल दिया है कि नहीं। फिर वो एक एक बात है एक बात।
to chair the session, and Professor G.P. Singh sir to co-chair the session. May I invite both of them to come to the dais? Professor Yakmi sir and Professor G.P. Singh sir. The invited speakers which are there in this session are Professor Vivek Kumar Gupta, Professor Sampat Kumar Bishwas sir, Dr. Adar Rahman Moila, and Professor Narendra Bhojak. Now I hand over the session to Yakmi sir and GP Singh sir.
आप ध्यान देना मैं बोल दूंगा Hello, good afternoon. Are we ready? Are we listening? Okay. So now you are going to have another session. They gave you tea and snacks, no? They have to recover that. So you must listen to the next session. The next session is, first speaker is my friend, Professor Vivek. He will tell you a number of new things. And at heart, he is a very innocent researcher. So try to follow what he did, please.
Good afternoon to all respected members on the dais and off the dais, all the participants. I am highly grateful to the organizers who have given me the opportunity to share my experience of research with you all. Thank you so much. So I have chosen this topic, disorder in the organic molecular crystals. So why I have chosen this topic? Because when our time, early 90s, when we were doing research, hardly there is any computational facility. So mostly physics people were involved in the structure elucidation. Nowadays, it is the journal requirement, you can say, every chemistry lab, whatever compound you are synthesizing, you have to supplement it with the crystal structure. Unless you do the crystal structure solution, it is not possible to publish your work and authenticate the things. So very basic requirement for a chemist is nowadays is to supplement their finding with the crystal structure. So it is the basic requirement of every lab. So what happens now, whosoever is doing this research, because now lot of machines are there in almost every very good lab, you can say. when we were doing research, hardly any diffractometer, I think 5 to 6 diffractometers in whole the country. So we have to keep in line, and we get a time of a week or so in every lab. So in a year, hardly we get 5, 6 samples. If 1 or 2 sample is already reported, our 50% work goes waste in that time. So what we were doing, we were manually plotting the RTAP, because it is not possible to plot the temperature parameters. So whenever we do structure solution in our time, we get a set of coordinates. Then we take a graph paper, we plot it on the graph paper and do the molecular plotting. Similarly, in Pecky diagram also, we do the manual plotting. So I have published papers in our time, PhD work in acta crystallographica C by manual plotting, because we don't have plotters. Printers now, you give your command, you get all the diagrams in 1 minute, I think nowadays. In the morning, you synthesize the compound, you put it in the diffractometer. By night, you are able to get the structure. And within a day or two, you are able to send it to a very good journal. But in our time, it takes a lot of time to make the things, because we don't have printers at that time. We have to do plotting, and for plotter also, you need plotter pens, which a common research scholar cannot afford at that time. So all the research work we at that time, early 90s, we were doing manually. And at that time, we learned the things. But nowadays, everything is done by machines. So my advice to the younger students who have taken this chemistry, or because nowadays very few people from physics background, they are doing structure solution, mostly chemistry people are involved. So you should have some basic knowledge about how we are finding the structures. One should not depend on the machines only. That's why I have chosen this topic. Because if you are solving 10 structures, you will get problem of disorder in almost 3 or 4 structures. Once you get a problem of disorder, if you don't have the basic knowledge of crystallography, you are unable to send it for publication. Basic requirement is now check safe. Unless you remove all the A level alert, B level alert, so it is very, very difficult to publish the things. It's okay, machine is doing its part. We are getting help from the machines, but alongside the machines, you should have basic knowledge how to solve the disorder. Nowadays, hardly any week passes, I get structures of solution for disorder solution from one part of the country to another part of the country. Because students who are doing this kind of work, they don't go the basic. Because it is not difficult to solve the disorder. Lot of programs are now there, which takes care of twinning, etc. But if it is a substitutional disorder, static disorder, first of all, one should be able to find out what kind of disorder it is. Whether it is dynamic disorder, it is substitutional disorder, it is static disorder. So unless you have the basic knowledge of this, twinning is taken care by the program itself. I think if there are crystallographers sitting here who are doing crystallography, this kind of work, they are able to solve the twinning problem. What when the disorder of substitutional kind comes, or whole molecule is disorder, then it is very, very difficult. Sometimes it takes months to solve a single disorder. That's why I have chosen this topic this time to say this. So this is what the power of programs and computer has made remarkable progress in the same period. There has remained one domain where crystallographers still spend a lot of their time, and this is when the structure under investigation is disordered. The very first hint you can get from the displacement parameters. So whenever you solve any structure, you get a set of coordinates, x, y, z, and then the displaced parameters. So equivalent isotropic temperature factor gives you a very first-hand information that the structure you are solving, whether it is disordered or not. Why disorder? Why disorder? From where disorder comes? Every unit cell has exactly the same orientation with all molecules in the same conformation. This is the basic definition of a crystal. All unit cell has the same environment. Only then we call a molecule crystallizing in a single crystal form. However, an ideal crystal does not exist. And in most real crystals, there are several lattice defects, and are impurities. So it is very, very difficult to get an ideal crystal. Whatever crystal you are growing, you have some kind of disorder present in it. Frequently, parts of molecule, it is not that, it is very, very rare that whole molecule is disorder. If a whole molecule is disorder, then there is some kind of problem in the data collection or something is going wrong. But part of the molecule, in some extreme cases, whole molecules are found in more than one crystallographic independent orientations. Sometimes when we talk of liquid crystals, they are very, say, rod-shaped molecules I am able to crystallize a liquid crystalline material in rod-shaped molecule. The length of the molecule is such that it is very, very difficult to have symmetric molecules in the unit cell. What we get independent molecules. But in one can distinguish 4 cases, more than one molecule per a symmetric unit. They are those molecules which are not sitting by any kind of symmetry. If there are 4 molecules in a unit cell, all the 4 are independent, then you have to solve each molecule differently. If they are related with some kind of symmetry, then you are only bothered with one molecule only. Then twinning is nowadays, earlier it is not, but nowadays very powerful programs are there. Twinning is taken care. In shellac itself, twinning is taken care. Then comes disorder, part of the molecule. Mostly central part of the molecule is not disorder. It is the side peripheral parts, the substituents, but whatever we have attached in the molecule, they show disorder. It is, although it is there central, sometimes central part of the molecule also, because of its rigidity, does not show any disorder, but some molecules show disorder. Or whole molecular disorder. Whole molecule disorder is very, very less. Now, this is the basic. From here, whenever you collect data, you solve the structure, and then simultaneously you plot it. So if your one terminal molecule is showing this thermal ellipsoid like this, so you can immediately say there is a disorder in the molecule. Then you have to resolve it, otherwise it will give error. In check safe, A level alert will come. Isotropic temperature factor is very, very high. It is not matching with the adjacent thermal ellipsoid. Now you can say anisotropic displace parameters of a disorder. This is the ethyl group. On the left without, and on the right with the disorder. We have solved the disorder here. We have bifurcated this part of the atom into 2 parts here. So now it will not show any disorder. If we have occupancy 1, it may be 70-30, it may be 50-50, depending upon how much disorder is present. If it is 5 to 10%, you can ignore it. If it is more than 20%, 30%, then you have to solve it and then refine it. If the disorder is ignored, the refinement program tries to describe both atom positions with one ellipsoid. If you try to ignore it, so both the positions, molecule is spending some time here, some time here. It is vibrating. It may be orientation depending upon different orientations in different unit cells. So giving rise to here, if the disorder is ignored, the refinement program tries to describe both atom positions with one ellipsoid. You can see from here, giving rise to a cigar-shaped probability ellipsoid. It is not an ellipse. It is a cigar shape. So this is the first-hand information from the R-type diagram itself that your structure is showing some kind of disorder. 3 major classes of disorder are dynamic disorder, static disorder, substitutional disorder. Both dynamic disorder, anyway, we can solve by taking the nowadays almost every diffractometer has low temperature facility. You collect data at a low temperature, dynamic disorder is taken care because vibrations will be very, very less and your disorder component will not show more than 5% disorder. But if it is static or substitutional disorder are mostly static kind of things. If the disorder is static, if you collect the data even at low temperature, So you are not able to resolve its disordered component. Both dynamic and static disorders are treated in the same way during refinement. Dynamical disorder is even frozen at low temperature, whereas static disorder persists even at low temperature. By collecting data at low temperature, there is no effect on substitutional or static disorder. Substitutional disorder describes a situation in which the same site in the two unit cells is occupied by different types of atoms. Suppose I have a substitution of a phenyl ring where it is chlorine attached to the phenyl ring. Suppose this is the chlorine atom. In one unit cell, it is freely moving substituent phenyl ring. In one phenyl ring, in one unit cell, it is sitting like this, other unit cell, it is like this. So in that case, it is a substitutional disorder. Chlorine is coming 50% occupancy at the right side, 50% occupancy at the left side. So that we call it as static disorder or substitutional disorder. A situation in which the same site in the two unit cell is occupied different types of atoms. This type of disorder that can be observed mostly with inorganic materials like minerals. So in order to cope well with this type of disorder, accurate knowledge of composition is very, very important. Because then thermal, if you don't have the substituent is chlorine or some other sulfur, so you should have some basic idea. Even from the shape of the ellipsoid, we can make out whether it is a low atomic number atom, you are giving high atomic number atom. If you are making carbon oxygen or oxygen carbon, ellipsoid will be very, very small or very, very large. So from the shape of the ellipsoid itself, you can make out whether you are assigning the composition to the molecule is correct or not correct. So that's why some basic knowledge to the crystallography is very, very important. Unless you know that if atomic number is less, what kind of ellipsoid we will get. If atomic number is more, what kind of ellipse we will get. So you are unable to resolve it. So we will take a very simple example here. Here you can see we are shining X-rays on the crystal. So crystal is a large number of unit cells, this side, downside, everywhere. That's why we call it as crystal. Suppose in the one unit cell, your molecule is like this. In the second unit cell, it is slightly rotating this substituent. Say it is OCH3. Methoxy group is there. In this case, it is slightly rotating like this. Fourth one, it is like this. There are number of unit cells. Slightly orientation change of 5 degree or 2 degree or 1 degree is there. So when you crystallize the molecule, you will get information. You are plotting it. You are plotting a single unit cell. You are not plotting a whole number of unit cells. So in that case, then it will be a combination of all the orientations. Now you can see your coordinate has to be here X, Y, Z. Now your coordinate distributed in the whole space here. Your now ellipsoid will be from this place to this place. Because in first unit cell, say methyl group is here, second unit cell methyl group is here, third unit cell methyl group is here, fourth unit cell group is there. So you will get a ellipsoid like this, not the point ellipsoid. So if now this ring is stationary, it is not moving. In the first unit cell is your ring is this, second is also this, third also this. If in the first unit cell your phenyl ring say is like this, second unit cell it is rotating like this, third it is rotating like this, fourth it is rotating like this, then your whole molecule is disordered. Not only single atom, all the atoms in the unit cell will be disordered, they will show disorder. Then we can say your whole molecule, complete molecule is showing disorder. This is a very general basic definition of disorder. Why disorder? Because this substituent is slightly rotating in the one unit cell to second unit cell to the third unit cell. Now the refinement program has number of constants. Those students who are doing crystallography, they are know number of constants and restraints are present. You can, for temperature, EDAP command you can give. Like this part command is there. It refines disorder by dividing the disordered atoms into groups. So whatever we got, normally we divide it into two groups. Even then, if there is disorder, we take the example of in the coming slides CF3 group, which is rotational disorder. It is very, very common. Wherever in the structure CF3 is present, it will always show disorder. So the occupancy of disorder groups are allowed to refine. We cannot keep the fixed occupancy. If you will keep the occupancy, because normally in refinement, we keep the occupancy as 1. So whenever we have to solve the disorder, we have to keep this occupancy as free. We have to allow it to refine. Maybe it is 70%, 30%, 20%, 80%. Unless you allow it to refine, your program will not run. As disorder is not expected at the early stages, it is in the final stage you come to know that your structure is disordered. Disorder in a later refinement cycle has to be inferred from the magnitude of equivalent isotropic temperature factor. So equivalent isotropic temperature factor is all the temperature factors, then there is a program. In our time, we were doing it manually. Nowadays, program itself take care of the equivalent isotropic temperature factor and it plots as a thermal ellipsoid. The shape and size of thermal ellipsoids is one of the most important indicators for problems with molecular model. So what kind of disorder is present? A very small ellipsoid indicates that the corresponding atom may be in fact be heavier than the one currently contained in the model. Suppose we have refined oxygen as carbon, your ellipsoid will become very, very small. So from there, you will see in the ring that 5 atoms, they are showing same almost size ellipsoid. One is very, very small. So you immediately come to know, if you have studied all this disorder, that you have put oxygen as carbon and vice versa. If it is carbon, you are giving it oxygen, yet then the size of the ellipsoid will increase. Elongated cigar-shaped ellipsoids are another sign indicating disorder. Flat, other shaped molecules, either they show pseudo-symmetry or incorrect space group. Suppose your space group is P21YA. You are giving it P21YC. Hardly there is a difference of 1/4 along one of the axis, motion of the molecule. So you should have clearly knowledge whether the space group is P21YA, P21YC. Otherwise, from symmetry point of view, very, very small difference. When you plot the equivalent diagram of a space group, hardly you will notice any change. But when you refine it, P21YN as P21YA, then all these problems will come. Now, suppose this, I have taken it as one of the example. Firstly, when I solve the structure, only these two, this is the terminal chain and hexyl chain. Say it is a liquid crystalline material. So only these two atoms, they were showing the disorder. Only 2 terminal atoms were showing disorder. All other atoms, they have the same, almost the same thermal ellipsoids. When I have resolved these two by bifurcating into 4 parts, 1, 2, 3, 4, then now you can see C104 is not showing disorder. Only C105 and C106 were showing disorder. Their shape is such that they are showing disorder. Cigar shaped. Now when I resolved these 2 atoms in the molecule C06, C06A, so now C104 started showing elongated shape. So now this means that this is also disorder. Now I have resolved it. I have bifurcated into 2 parts. Now the disorder now has gone from C104. Now you can see C103 is not that much elongated, but still it is showing some kind of small disorder. Maybe it is 50%, it may be 30%, no, it may be 20%. We have to resolve this also. We have resolved this. Now you can see C102, it is almost showing nil disorder. Even disorder of 5% we can ignore. So you have to do systematically the refinement. It is not that only 2 atoms are showing disorder. You will resolve them and leave it. Then the next you have to see what is the temperature factor. Then you have to resolve this. After that you have to see the earlier one. So now you can see the NXL chain. We have removed the disorder from 1, 2, 3, 4, 5 atoms. We have bifurcated 5 atoms of the chain into 10 atoms with occupancy maybe 60, 40, 1 is 50, 50, 1 is 30, 70, like this. This is how disorder is resolved in the long chains. Now I will come to the example I have shown earlier. If here I have put chlorine, in other case, because now this bond, it will rotate from unit cell to unit cell. In one unit cell, the molecule, this 5-membered ring, sulfur molecule, sulfur atom is sitting like here. In the very next, it is showing at this place, because phenyl ring, it is free to move. It will move like this. Now, whenever you will solve the structure, you will find here disorder in this molecule as well as this molecule. Now, this atom is 50% carbon, 50% sulfur. This atom is 50% carbon, 50% sulfur. Earlier it is 1 occupancy of carbon, 1 occupancy of sulfur. But both the atoms, they are showing disorder. So this is static disorder, or you can say it is a substitutional disorder. Okay, sir. Disorder thiophene ring as seen after refinement and a disorder model with the original position. Bonding axis is rotating by 180 degree. So mostly when phenyl rings are here in this also same ring. Here there is no problem. There is also situations like this. But here disorder is very, very small, 5%. When we solve this molecule is showing disorder of 5%. This molecule is showing disorder of 50%. So you can see, even though a sulfur atom takes the place of a carbon atom and vice versa, carbon is taking the place of sulfur in the other unit cell, because unit cell is a large number of unit cells in one direction, in other direction. So the result of crystallization process, the different orientation of thiophene ring are a result of the crystallization process and would therefore be rather classified as a static than a substitutional disorder. Now solvent disorder, you have seen that mostly DMSO, whenever you crystallize your molecule in DMSO, 90% DMSO will come as a disorder. Or some water molecules in protein crystallography, those who are doing crystallography in proteins or in large molecules, macromolecules, water molecule is showing disorder. Disorder structures can also be classified on the basis of what part of the structure is disorder. As a rule of thumb, it may be stated that smaller the molecule that we want to look at, the bigger the probability that it moves with the temperature. Small parts of the molecules, the side substituents, peripherals, thus disorder in solvent, because if molecule is bigger, water as a solvent is very, very small. So water will show the disorder, not the bigger molecule. Thus disorder in solvent molecules tend to be more frequent than disorder in bigger molecules. Sometimes bigger molecule as well as water solvent, they both show the disorder. This problem is of particular interest and importance in macromolecular crystallography and in protein crystallography, where water component is almost 40%. Now you can see here, this is very interesting molecule I have solved. It is a steroidal molecule I have taken. 2 solvent molecules, because this is the acetic acid. When I have solved all the molecules of acetic acid, they were showing 50% occupancy, 0.5. This molecule is showing 100% occupancy. But 1 oxygen of acetic acid solvent, it is showing 1 occupancy. So it is very, very difficult to resolve it. It took me months to resolve this. So now what happened? This oxygen has 1 occupancy. All other atoms of the acetic molecules, they have 50% occupancy. No, it is not the oxygen of acetic acid, 50% occupancy of water solvent also present. So this oxygen is 50% belonging to the acetic acid, 50% belonging to the water solvent. Atom O28, this one, of CH3COOH acetic acid is further disordered into another position, O28 with the refinable occupancy. Further, this oxygen was showing disorder. We have resolved it. So in structure refinement, atom C26 has 100% occupancy while all other atoms. So unless you have the knowledge of crystallography, no one can solve this kind of disorder, where one atom of a particular solvent is showing 100 occupancy, other is showing 50% occupancy. Then you have to realize why it is coming so. So then the idea came, it may be a water, half water solvent. So then when we did, R factor drastically came down. Otherwise, your R factor will stuck up to 10%, 11%. You are unable to get 4-5% disorder. Sir, hardly 2 minutes. So because this whole molecule is showing one occupancy, your solvent is showing 50% occupancy because it is sitting on the two-fold axis. 50% belonging to this unit cell, 50% belonging to the other unit cell. So two-fold rotation symmetry is present in the acetic acid solvent only. Partial fragment disorder. Now, your whole molecule is stabilized 100% occupancy, but this acid toxic, 3 acid toxic substituent, one of the oxygen of 3 acid toxic showing disorder. So we have bifurcated into 2 parts, O22 and O25. Looking at the magnitude of displaced parameters, it can be shown that U values tend to be smaller in the center of the molecules, but however, acid toxic group is showing large your thermal parameters. So this is the example of your whole molecule is showing disorder. But it may be, sometimes your data collection may not be correct, or there may be other reasons in that case. So CF3 molecule I have talked earlier. So wherever CF3 molecule is present, it always show rotational disorder. So whenever you solve it, you will get 3 more peaks. Then you have to resolve fluorine into 2 components. Sometimes fluorine has to be resolved in 3 components. So disorder model over 2 positions here, same, but fluorine atom here you can see it is complete circle. We have made refinement as isotropic. When you will make it anisotropic, it will become ellipse. So I will skip it because of time constraint. So this is another molecule. I am still working. So it is already reported in NACTA in the year 2007. This molecule here, they have reported it. So they have shown it as a substitutional disorder, this oxygen atom at this place as well as this place, because it has the same environment in this chain. In one unit cell, it is coming here, other unit cell, it is coming here. Same molecule when we have taken for structure solution, I am still working on that. So what all parameters are same, our unit cells are parameters are same. In my case, this ring is coming disorder. I have resolved the disorder of this 6-membered phenyl ring. So now in this case, in my case, it is not the substitutional disorder. Oxygen is not taking 50% occupancy or 50% occupancy. It is ketoenol form. It is here OH group, it is a keto group. 50% occupancy of the keto group, 50% occupancy of the enol group. Moreover, at this place, I am getting one more peak. When I solved it, it is coming as NH3. Still, I have not yet sent for publication. I am making it to be 100% sure that whatever it has crystallized. Now, in my case, this is one molecule as keto form crystallizing in one unit cell. In other unit cell, molecule is crystallizing as enol form.
Vivek, time ho gaya. Time.
Last slide, sir. This is. In the third unit cell, it is crystallizing with the NH3 group. So all the 3 molecules, they are crystallizing as one molecule. Sir, last. So this is, I have put in this structure number of restraints and constraints you can see. So unless you do some kind of basic crystallography, you are unable to do this kind of constant and restraints in the modeling of the molecule. So my advice to the younger generation is, for resolving disorder in molecules, basic chemical knowledge and understanding of the fundamentals of crystallography is very, very important. The answer to the question of whether a specific disorder is worth refining as much based on experience as the assessment of data quality and difference density maps. Thank you. Any questions from your side?
One question.
Thank you, sir. Thank you, sir.
Next talk is by Professor Sampat Kumar Bishwas. Hello. Sitting there. Yeah. So, क्या हुआ? कुछ confusion हो रहा है. I thought he was ready sitting with his laptop चालू. डाउनलोड हो रहा है शायद कुछ डाउनलोड हो रहा है. Professor Sampat Kumar Bishwas. So everything is loaded. Yeah. Thank you. And they already know you. You are the boss of the session. Eh? All 30 minutes. 30.
Anyway, so today I thought that since it's a conference of condensed matter, so let me see if something could be done on my work in relation to the condensed matter. So what we have found that we have done a little bit of work on armored ceramics. Because you know the ceramics is a material which can defend the bullet or the projectile very efficiently. Because earlier it was metals.
Sampat.
Earlier it was metals, and now it is transforming to ceramics because of the lightweight. So apart from that, there are many other advantages as well as a little bit of disadvantages also. So still not, it is not very clear how the ceramic failure takes place, and to understand those failure mechanisms, we need to work very carefully, and we have to handle these things in a very efficient way. So let me first tell you those who do not know what is ceramics. I think everybody knows what is ceramics, but basically it is an inorganic material which are processed at high temperature. So now the definition of ceramics have changed. So these are basically including carbon compounds, carbon as well in the ceramics, like carbon nanotube, graphene, etc. So traditionally ceramics were made like terracotta and all these clay, feldspar and quartz made from the clay, feldspar and quartz. So those are all traditional ceramics. You have seen it a lot, and its technology is 3,000 years back. It's a very age-old process. But with the advent of the modern technologies, you got advanced technologies, and for the advanced technologies, you need materials which cannot satisfy the normal conditions. So these materials are called advanced materials, and it is processed also by the advanced technology. That is a very interesting thing. So these advanced ceramics are now coming in different applications. So one of them is armor. Now, these ceramics are aluminum oxide, silicon nitride, silicon carbide, barium titanate, calcium fluoride, silica, and there are a lot of inorganic compounds. You can make it ceramics by processing at the high temperature. Now let us see how the ceramics fail. If you take a ceramics and drop it, it will break. So its fracture toughness is very low. You cannot compare the fracture toughness of a ceramics with metals or polymers. So its fracture toughness is very low. But even then, when a bullet impacts the ceramics, the bullet fractures. That is the most important thing. The bullet fractures and get crushed. So that is the reason why ceramics are applied in the armor. So a lot of researches are now going on around the world to understand the mechanism of failure and how it is happening. Now here comes the condensed matter physics, which helps us to understand the mechanism of the failure. If you look at it, you can see in the diagram, this is the projectile. When it hits the ceramics at a very high velocity, that means it has got a very high kinetic energy, the tip of the projectile deforms and the ceramics also breaks. Now this breaking of ceramics, if you can delay it, you can restrict the failure. So the tip of the projectile, when it hits the ceramics, it creates a conical shape crack. So these conical cracks are quite common to anything on the impact load and under the shock wave conditions. And shock waves are generated within the ceramics as well as within the projectile. Now, the sign of the shock waves are different in the ceramics and in the projectile. It depends upon how the impedances of the two materials are. Impedances means density and the velocity of sound waves within the materials. So this is the way how the ceramics fails. Now, in the case of ceramics, aluminum nitride, silicon carbide, and are the main. These are the two main ceramics which are advanced ceramics, and which is occupying the states of the ceramic armor materials. Now we have carried out a little bit of work on aluminum nitride. See, aluminum nitride is a woodside crystalline lattice, and it is a hexagonal woodside crystalline lattice, and it has a very interesting properties. If you apply confinement load in a aluminum nitride ceramics, what you will get transition of the properties from the brittle to the ductile. It's it's very new invention, and people have found that when you apply confinement load and then you hit it with a shock wave, you'll get the transition from the brittle to the ductile. So this brittle to ductile transition takes a lot of energy. It consumes a lot of energy of the bullet, and it helps to protect the bullet. So we carried out an experiment with two different ceramics. One is aluminum oxide, the other is aluminum nitride, and wanted to see how this varies with the type of the ceramics, with the chemical composition of the ceramics. So one is ALN, the other one is Al2O3. If you can do, those two have got two different crystal structures. One is having rhombohedral crystal structures, the other one is having hexagonal crystal structures. So our projectile was about 10.57 gram weight, and it hit with a muzzle velocity. Muzzle velocity means when it hits, if you take a gun shot, you can change the muzzle velocity and by changing the composition of the explosives. So by changing the muzzle velocity maximum, it can go up to 847, and we did the experiment with the highest muzzle velocity of the projectile. It is about 847 velocity, and it happens with any AK-47 bullet. So that was our technical interest. Now this is the target which we took. This target is made up of aluminum alloy A, on which we have placed a fiberglass material which is surrounding the ceramics. This ceramics is denoted by C. Then this C portion is hit by the bullet, and later on we have modeled it in the numerical simulations, and we did the work. Now what I wanted to show you is that projectile velocity, when the projectile is hitting the ceramics, gradually velocity goes down. Because it goes down, it breaks the ceramics. At the same time, its own velocity is going down. So this can be simulated. This can be experimentally verified. This can be simulated as well. So we carry out the simulation work. Now if you look at this, you can find that there are two areas. This is the maximum velocity of the bullet. It is going down. And in these two materials, where it stops, this time is different. In one material, it is stopping within 42 seconds, 42 microseconds. The other one, it is stopping at a much higher time. So much longer time, sorry. So this time difference, what it plays on the property of the ceramics. Here comes the question of ductility within the material. So if you can increase the ductility of the material, you can get a lot of energy absorption as well. So then we looked at the microstructure of the impacted ceramics. What we found that ceramics is, as I told you, ceramics is a very brittle in nature, and that is due to the high Peirce number of stresses. And this brittleness is only because ceramics contains dissimilar ions. While metals have consist of similar type of atoms, in case of ceramic crystal structure, you get dissimilar ions. So these ions, when it moves to form a dislocation, what happens? Positive ions comes in close to the another positive ion and it repels. Similarly, negative ions has got an attraction with the positive ions. So naturally, the bonding between the ions is very strong. So finally, as a result of which what happens, the Peirce-Navarro stress, which creates the shear of the crystal structure, is very, very high. So ceramics are not at all ductile, it is a brittle in material. But when shock waves are coming, this huge shock waves at the shock waves pressure of 50 gigapascal, 50 GPa or 40 GPa, now this brittleness doesn't play any role. What happens that ions are forced to move from one place to the other, and you get dislocations like this. And this is not only dislocation, you get the domain boundaries also. What we have taken the transmission electron microscope of the failed sample that we have carried out one typical experimental arrangement so that the debris after the impact could be collected, and this debris was analyzed further for future, to understand the mechanism of failure. So from that debris, we have taken the this sample, the thin section. We have seen here the Shockley defect, and Shockley defects are coming, and this Shockley stacking faults originated from the dislocations. You can see this is present in the original material. So the original material is also very important. It is present, but in very minor quantities. But when it is shocked, you can see lots of domain boundaries are also there. These are the antiphase domain boundaries, and these are caused due to local shear stresses. So it absorbs lot of energy, and this is a dark field image. You can see clearly the domain boundaries. So this absorbs a lot of energy of the impacted bullet. So this happens in case of aluminum nitride, which is prone to ductility at a considerable confinement pressure. Next, another important ceramics is silicon carbide. The silicon carbide is a very interesting material, as well as aluminum nitride. It can be applied in lot of applications. So one of them is the armor applications. Why it is so? It has got two crystal systems. One is woodside, it is hexagonal, and the other one is cubic, that is sphalerite structure. Now, in case of inorganic materials, what happens? You cannot say hexagonal or you cannot say cubic. You have to identify one analog with it. So here it is sphalerite, it is in the cubic lattice, and the other one is the woodside, it is in the hexagonal lattice. So these two crystal systems of the ceramics, apart from that, it has got different polytypes also. Polytypes means the stacking of the ceramics are different. I'll show you later. Before that, I want to tell you that there are 200 polytypes of silicon carbide. So most common polytypes are 2H, 6H, 4H, 15R, and 3C. This 3C symbolizes the cubic form. The 2H, 4H, 6H are hexagonal form, I'll show you how it happens and what are the structures. Now, one important thing is that diffusivities of, since these are covalent, so diffusivities of silicon and carbon within their lattice is very low. So you have to apply pressure, high temperature additive to prepare these polycrystalline materials. Now we are dealing with the polycrystalline materials. We are not dealing with the single crystal materials now. So it has got a very high Vickers hardness, about 27 GPa we have got. So it is very high at 1 kg load, and it has got a high sound velocity. That is most important. This high longitudinal velocity as well as transverse velocity within the ceramics. Solids have got much higher sound velocity. That is very important for armor applications. Now, and as well as it has got a low density, about 3.21 grams per cc. Now, regarding the polytypes of silicon carbide, you see these polytypes differ due to, the properties also differ due to the different polytypes. So, in these polytypes, what happens? The stacking of 111 silicon carbide bilayers on the, and as well as, 0001 of the hexagonal bilayer. It has been found that during processing, you have to add some aluminum or boron or carbon within the material to get it densified to a maximum density, say about 98%, 99% relative density. And you have to add some metal ions like aluminum. What happens? This aluminum goes into the 6H structure, and it converts it to the 4H structure. It creates fault within the lattice, and it then converts it to the 4H structure. So this polytypic transformation is very important in this silicon carbide ceramics. So there are existence of Shockley stacking fault, and there are these are in somebody questions that whether Shockley stacking fault is the only stacking fault, but there are Frank stacking fault as well as present in this material. Now let us see how the polytype structures are there. You can see this is the pure 3C. These are the 3 stacking layers A, B, C. Then this is the 2H. Then this is the 4H. You've got 4 ions. There are 6H. You have got 6 ions, and so on and so forth. Now these are the stacking faults present in the 2H, 4H. And 6H structure. Here it is a case of 6H structures in the zone axis 1, 1 towards 0 and the basal plane. And you get different. Just I wanted to show you that how these stacking faults are in silicon carbide. Now, when we apply shock, as I was telling you, the microplasticity appears. Microplasticity means the ceramics becomes more ductile, and this was first reported by some people like Longi. Then some people have also analyzed the dynamic plasticity of silicon carbide during compressive loading. So these are the previous works I wanted to mention you. So here what happened, that lastly, some people have found that amorphization has been taking place. That means when you are hitting it with bullet, when you are giving it extra shock pressure, shock pressure, the crystalline to amorphous formation, phase formation is there, and from there recrystallization also takes place. These were the mechanisms, and some people have observed it. We will also show you how it happened in our case. So, physical mechanisms behind the inelasticity is still not very clear. Most of the earlier studies have been carried out under the 1D strain or 1D stressed conditions, but in case of actual armor, it is the multi-axial strain which plays very important role. So we have carried out our experiments with actual heat of the bullet, recovered the soft specimen, and then carried out the further characterizations. This has not yet been done so far. We have not got any report from anywhere who have done this. So what we have taken the starting powder. If you look at the composition, you can find the 3C composition is only 5.5. Mostly it is 6H powder. So we have started with the 6H powders. Now, when we prepared the ceramics after sintering or hot pressing, what we have found that 6H quantity of 6H is reduced while quantity of 4H has increased. This is possible for a polytypic transformation from the structure 6H to the 4H. And later on, some cases where you add a different additive, what you find that your polytype ratios are changed. In this case, you can find in the P2 samples, mostly 6H variety is maintained and no, I mean, very few transformation is there to the 4H and 3C. This is the original ceramics I am talking about. Then I will show you how it happens after the impact with the bullet. Now, inelasticity of ceramics was, first studied by planar shock experiments. Planar shock experiments means you apply a planar wave to the ceramics and then follow the response. And these responses are followed by means of a manganese gauge or a piezoresistive gauges. And you will find the particle velocity, time, and you get a shock Hougonio also. So Hougonio characteristics are very important in case of armored ceramics. Now you look at this thing, about in 1979, it started long time back. So I will mention only one paper where they have shown that initially very high rise of stress is there, but gradually it deviates from the linearity. It is called, that's the reason why it is inelastic, and it retains its strength at a very high level after it breaks down finally. So this retention, we are very much interested. So we are going to analyze our materials from this retention value. So these are our experiments, and this experiment has been carried out in TBRL for the first time in this country. So this experiment was carried out in TBRL. So our samples, one sample data I am showing it now. You see, the inelasticity comes from this level. When it starts deviating from the linear elastic mode, this point is called elastic limit, named after the scientist who discovered this thing, that is called Hougonio elastic limit, or HEL. So Hougonio elastic limit is a parameter by which we can judge ceramics from one to the other, which is very effective. Now, Hougonio elastic limit in case of this is very high, about 13 GPa. We have found in case of silicon carbide. And further, if you look at the tank, it retains the strength. The stress rises very high, and it retains it for some time. And these are called the plasticity region. So we will then look after the plasticity region. So these are the Hougonio elastic limit we have obtained for these two ceramics. One is with the aluminum addition, the another is on the aluminum nitride addition with the corresponding solid solution. And this is a different mechanism. I am not going into details into it. But value of the HCl changes with the material. Means the composition of the materials is very important. Crystal structure of the material is another important criteria. Then alignment of one crystal with the other, called the grain orientation, is also very important. So in case of one, we have seen 11.27 GPa. The other one is about 13.42 GPa. Also a little bit on the how are the things. So these are the two microstructures. You can see that here longer grains are obtained. These grains are mainly, we believe, are 6H grains, and this elongation has been taking place in one microstructure. The same silicon carbide, while processed in a different way, the grains are become very smaller. So we carried out our experiments with these two silicon carbides, preferably in line with the commercial armored silicon carbide available in the market, international market. So we developed the material here, and then we carried out our further experiments here. So grain sizes of these are very small. Here the grain sizes is, heterogeneous grain sizes you can find. One is longer, the other one is very small. Now let us see how it happens. Now, we have analyzed the XRT samples after the impact. We can find that initially we have started with 51.19% 6H variety. It changes to 78.9% while the 4H is reduced as well as 3C is reduced. That means these phases have transformed with the help of shock wave to 6H variety. So that is a very important observation we could find out. And this observation was also made some people earlier in the year 2000. So this is in case of another variety of silicon nitride. It is not only that, we will find another thing. Then what we did, we carried out transmission electron microscope analysis with these materials. Now, these are the two microstructures, and these are the debris formed after hit with the bullet. You can easily differentiate between these two materials after the bullet hit. One has got very long, very big fragment. The other one is very small fragments. So we took out the fragments near the bullet hit region, and we then carried out sections for the TEM analysis. In this TEM analysis, you can find this is a very long grain I wanted to show you, and these are very small grains attached with it. In the other case, it is very smaller grains. What I wanted to show you that the surrounding small grains are also very important. It has got a lot of defects, and these defects have been analyzed here. This is a bright field TEM micrograph of different tilt, under different tilt conditions to reveal the microstructures more efficiently. And this is the SAED pattern. This SAED pattern is a double diffraction pattern, wherefrom you can analyze that the two different crystals could be identified from this. One is the 6H variety, the other one is the 3C variety, and this is a typical spot patterns of any stacking fault. Now, another important area is where we have found is that amorphous phase, a diffused rings we can found from this TM. This amorphous phase is very important area, and probably we presume that this was present during the sintering process and after, because other materials didn't have this amorphous phase. This is a 3C variety. I'm not going to details of it. What we wanted to say is that lot of dislocation activities were there during the shock process, and while these were in the plasticity region, and these dislocations create defects, which you can find later. I am showing you. See, if you look at it, typical Shockley defect, you can find one dislocation creating the defect here, the other dislocation creating another stacking fault here, third dislocation creating the third stacking fault here. This is a typical Shockley defect created by the dislocation and by the shear stresses involved and applied to this material during the shocking. So, conclusion is that microplasticity with defect creation could be observed in the grains of both aluminum nitride and silicon carbide. Then mainly Shockley stacking fault we could identify. We didn't find any Frank stacking fault or any other extrinsic faults. Antiphase domain boundaries could also be observed in aluminum nitride. These defects ultimately lead to micro fissures within the ceramic grains. Tiny little crystals could be observed in the recovered samples. So dynamic recrystallization is the main process of microplasticity, and this has never been reported still now. So we are going to communicate it very soon. Thank you very much for your attention. Our main collaborators are from CSIR, CGCRI, Mr. Tarit Chakraborty, Dr. Jiten Ghosh, Dr. Sandeep Baisak, Dr. Atiyar Ranjan Mulla, and then MNIT Jaipur, my students are there, Dr. Mr. Abhishek Boy. He was a BTech student, and during his during his graduation project work, he did this transmission electron microscopy work. Wonderful. I mean, I am very happy with this type of students. Then Wadat Mullah, Amar Patnaik. Lastly, I want to acknowledge my thanks to the TVRL people And this is because of Dr. Manjeet Singh, Director of the TVRA, and the Ipsita Viswas, Devarati, and PC Gordon. Thank you very much. Thank you all for a kind attention. Any questions?
So we have time for 2 questions. Who wants to ask a question or clarification? So let me say something. Can we say this whole work, what you have explained, is geared towards some very definite applications? In short, the whole thing.
Actually, this was created, this was initiated with one of the projects, along with the suggestions from DRDO, to develop some armor ceramics material. Because in that time, the country was not having this type of ceramics. So we initiated our program with the aluminum nitride. Then we did a lot of work, even creating armor. We gave it to the ordnance factories for testing, and they found it very nice, very okay. And now subsequent things were there. In the meantime, lot of things are there.
Good.
Okay.
So anybody? So let us thank the speaker once again. Now we move ahead, and we have the next speaker, Dr. Atayar Rahman Mullah from CGCRI, Central Glass and Ceramic Research. There, a senior scientist, so he will give us some facets onto his achievements. Thank you.
Oh, you. So, you were visited by Sheikh Kumar many times. Yes, yes. He was our assistant. Fond of going to CGCR. Yeah, very good. There's a problem. He was also maintaining a flat close to the Calcutta. So good afternoon, or I think. So I will be talking on some different topic. It's on glass, and that is very close to our heart. We use every day different kind of mobiles. Mobile is having display, and we want a stronger display that it will not break. So scratch resistant, stronger display, how we can make. So that I am just going to present you. Okay. So it is basically some advanced version of Gorilla Glass. So all of you heard of Gorilla Glass, right? Gorilla Glass, you have idea some? So we are trying to make some kind of glasses which will be unbreakable and much stronger than Gorilla Glass. So how we can do that? So before going into the topic, I just want to give you a small introduction, what is glass? Because this audience may not be from the glass background. So you see there are 3 kinds of materials, metals, ceramics, and polymers. So glass belongs to which category? Any idea? Glass belongs to which category? Ceramics, right? So mostly glass belongs to ceramics. So we can make glasses out of ceramics. So all these glasses, window glass, bottles, containers are ceramic material. But we also know that there are glasses, metallic glasses are also possible, right? So bulk metallic glasses are also possible, and polymeric glasses are also possible. So take home message is that you can make any material, you can convert into glasses, any material. If you can melt it, and if you can cool it faster than its rate of crystallization, you can convert any material into glasses. So it is not confined to metals, ceramics, or polymers. So any material you can convert to glass, and you can get some unusual properties. So this is typically a glass plant, how it looks like.
So this is a Saint-Gobain. You heard of Saint-Gobain glass? So this is a Saint-Gobain factory in Sri Perumbudur. And the size of this is the size of a car. So it's a big size, few kilometers size. If you want to see how the float glass is manufactured, I just want to show you a small clip. So this one. So how float glass is manufactured in industry. So 1,000 ton glass is produced per day. So this is a fully automatic plant, and glass is melted and floated on a molten tin bath so that you can get a uniform thickness and sizes. So this is raw materials fed into the glasses, furnaces, high temperature furnace, and glass is melted, and after that it floats to the molten bath to get a uniform thickness. Sound, no sound? Okay, you can move it forward a little bit. So this is a typical glass plant, closed glass plant. I think you have not seen. So I just wanted to show you how glass is manufactured in the industry, typical industry. Float glass. You can move it forward a little. So basically the glass is manufactured in the industry. So it is made fully automatic so that human touch is not there, because it creates a lot of defect in the glass. And because of these defects, glass is having unusual strength, and that we cannot get basically. That I will explain later. And bottle glass, how the bottles are made, just a small clip I want to show here. The bottle glass, how it is made in the industry. Just what I have been showing this bottle glass. The container glass, how it is made. It's called individual section machine. So in one glass plant, you can have different varieties of glasses you can make. So small gob is falling from the top of the furnace, and there is a press and blow method we call. And through press and blow method, we can shape different kind of glasses, different kind of containers, mostly wine bottles and different bottles, beautiful looking. So all these are made in the IS machine, individual section machines. So you can stop it. Okay, so we understood that any material can be converted to glass if you can melt it and cool it faster than its rate of crystallization. So you can have bulk metallic glasses, now it is possible, which is having unusual strength. So glass is basically a non-crystalline solid, and if you see that crystal, this is a quartz crystal, it has long range periodic arrangement. But in case of glass, this long range arrangement is missing. We call it short range order. So if you can melt a glass and you can avoid the crystallization, at this point, we end up with a supercooled liquid. We call supercooled liquid. It is a liquid having it's basically a solid, but having a liquid structure. So that's why we call it supercooled liquid. Sorry. So here, one thing just I want to point out that if you can make a glass, same glass composition, if you cool it very fast, and if you cool it slow, you will have different kind of volumes. So it will have different density. So those, depending on the cooling rate. So same glass composition, different density you can obtain. And that actually used to engineer the glass surfaces to make it much stronger. So that I will explain later. So this is basically, these are the things, 5 kind of oxides we use for glass melting. I'm not going into details. And display, you know, there is a huge market. There is a market of around 1.42 billion US dollar. It is projected to rise to 1.97 US dollar by 2028, and there is a huge growth rate of CAGR of 5.7%. And there is no Indian manufacturer. Now there is a one company, India is manufacturing, but mostly it is from USA and China and other companies, they are manufacturing. So India, there is a potential for developing such kind of glasses. So one question is I just want to ask to the audience, can glass be made stronger than steel? Is it possible? What do you say? Possible or not? So it can be made possible. I will show you. If you see the theoretical strength of glass is 35 GPa, 35 GPa, and strength of steel is 0.4 GPa. So it is a glass theoretically 100 times stronger than steel. But we don't get that kind of strength because glass is having small micro cracks all over the glass surface because of the handling. So if you can achieve 1% of the theoretical strength of glass, you can have a glass as strong as steel. So glass can be easily made much stronger than steel, and there is a potential. You can make it, and that's why Gorilla Glass is upgraded. Now it is 7th and 8th generation. Gradually they are upgrading and they are making much stronger glasses. So glass, there is no other choice for display application because of its transparency. There is no other material, and also hardness. And mechanically weak and brittle, that we have to address. If we can make it unbreakable glass, then it's something will be very, very phenomenal. So there are different strengthenings actually to strengthen the glass surface to suppress the minimize the defects in the glasses. There is micro cracks in the glass that actually reduces its mechanical strength. And I just want to show you that there are different techniques, like lamination is also one of the techniques. Multi-layer glass is used, and those kind of layers actually used for making bulletproof glass and skywalk. I just want to show you one image. Oh, sorry. So this laminated glass is used in the windshield, car windshields. For bulletproof application, multi-layer glass is used, but there is nothing but a bulletproof glass. And also we use, the skywalk is made of multi-layer laminated glasses. So those are that kind of reliability we have with glass, that you can walk through the skywalk, standing at few kilometer height. Okay. So lamination is one technique. Then another is the thermal tempering. So most of the windshield of car is made thermally tempered to strengthen the glass surface. And a new technique I'm just talking about is basically, I will say, it's a glass ceramics that I will be mostly covering today. So glass ceramics is having huge potential for making unbreakable display. And this ion exchange technique is used for in Corning Gorilla glasses. They use ion exchange technique to strengthen the glass surfaces. They basically create surface compressions. So these are the Gorilla glasses we use mostly in mobile and tablets and this smart watches we are having. So these are the technique, mostly lamination, thermal tempering, glass ceramics and ion exchange are the techniques mostly followed to strengthen the glass surface. So I just in the beginning I was telling that if you cool it at same glass at different cooling rate, you will end up with different densities. If you cool it faster, you will have a lower density. If you cool it slower, you will have a higher density. So what happens, thermal tempering, the glass blocks is exposed to a high temperature and suddenly quenched it. So as glass is a thermally insulating material, what happens, surface cools very fast compared to the interior. So there will be a different kind of density than interior and the surface. So because of the density difference, it pulls the surface and creates some kind of compression, and that strengthens the glass. So that we call thermal tempering. So in chemical tempering, what happens exactly? There is a sodium ions here in the glass, and that is actually exposed in the potassium nitrate solution at high temperature. Smaller sodium is replaced with the potassium, bigger potassium ions. So this bigger potassium ions actually creates a surface compression. So small cracks that is already present in the glass surface, that is actually compressed, and it gives you a lot of strength in the glass. And Gorilla Glass is mostly relied on this kind of technique, right? So I will show how Gorilla Glass is made also. I will show. So this is basically Gorilla Glass, and I will be talking mostly on glass ceramics. So glass ceramics, that also I will explain, but essentially glass ceramics is glass. Within the glass, you are having small crystals. So small crystals are dispersed in the glass. It helps deflecting the cracks, and it strengthens the material further. So it is more stronger than the glasses, normal glasses. So actually, Gorilla Glass was made in 2007. So this man, you know, his name is Steve Jobs. So he actually made a call to the Corning CEO. Corning is a US giant glass manufacturing company. So he told, before launching the first iPhone, he told, can you make some glass which is crash resistant and unbreakable, or much stronger than the normal glasses? So that Corning took up the challenge, and they produced the glass in 2007. Right, and now today there is 6 billion users worldwide of this kind of Gorilla glasses. So how this glass is made actually, it will be interesting for you to see here, how this glass is made here. You can show this video. This is a Corning factory in USA, and it's a very interesting technique. I've just, sound.
हाँ ये तो उसमें से शेयर कर रहा है ठीक है वीडियो का ऑप्शन अरे ऑडियो दे रहा हूँ ना यार उनको सो स्क्रीन पे शेयर करना है हाँ सर ये स्क्रीन शेयर तो हो रहा है साउंड इधर शेयर करते हैं वैसे
From beginning.
In the middle of grass and bourbon country in Harrodsburg, Kentucky, is Corning's oldest glass factory.
माइक बंद कर लेते हैं माइक ऑफ
And then in the 1980s, we transitioned it to enormous business for us.
Steve Jobs made a call to the CEO of Corning and asked the company to create glass that could withstand scratches and breakage for a new Apple product. Before that, phones were typically covered in plastic. Corning quickly developed Gorilla Glass. And this factory went through a complete transformation.
We leveraged the fusion forming technology to make Gorilla Glass, to make the first composition of Gorilla Glass here in Harrodsburg. Since 2007, I could say that the Harrodsburg plant has undergone a number of innovations to support all of the new Gorilla Glasses as they transition to stronger, more scratch resistant, and more durable glass.
The same company that developed the glass for the Edison bulb in 1879 is now making the glass that covers 6 billion smartphones, tablets, screens, and wearables worldwide. We got a rare look inside Corning's flagship Gorilla Glass factory to find out how it's made. Robots and massive machines are continuously making glass 24/7 here. It starts with a mix of materials that are sourced from all over the world.
Here we are in the mix house. This is really where the heart and the start of the Gorilla Glass composition begins. Some people may think the glass is just sand, but it really isn't. There's a lot of complex science that goes into Gorilla Glass specifically. It is extremely important that we have a strong and robust recipe. So as you think about how you make your cake at home, similar to that, we have fine-tuned and evolved the process for making glass over decades. What you can see at the facility are screw feeders and feeding systems that will take that material and transition it into a large bowl where it will be mixed so that we ensure that the mixture is homogeneous and can create the best glass possible. One bag, as you see here, once it's filled, will actually turn into thousands of sheets of Gorilla Glass.
The raw material then travels up 7 stories to the top of the factory, where it enters a giant oven turned up to more than 1,800 degrees Fahrenheit. Corning did not allow us to fill the oven. for fear that competitors would figure out its secret sauce and take a chunk of its $11.4 billion in sales in 2018. But it was an impressive, giant machine that melts the raw material to hot molten glass over the course of days. The laminated glass is closed down to several stories with cools and strengthens in a process called fusion forming.
To describe our fusion forming process, if you imagine a frog, and the glass comes into the top of that frog, and then flows over the edges of the frog down to the point where it fuses together. It's really fusing together in the air, and nothing touches that pristine surface. So both sides of the glass are seen as it transitions down multiple stories to the bottom of our process, where it's then stored and separated into discrete sheets. Fusion forming process is capable of making thicknesses of glass over 2 millimeters down to 100 microns or down 1 millimeter, which is just larger than the size of the strand of hair.
The glass comes out of the fusion process in sheets that are cut as big as 9 feet by 10 feet. Only robots touch the glass throughout the process. And sometimes the robots make mistakes.
So as the glass transitions to the final step before it gets shipped and packed, realize that the glass has never been touched by human hands. When it gets to this final step, we laminate the glass to protect it both for shipping and to allow our customers to handle the glass as they pull the sheets out of the crates. The sheets are then transitioned into crates where they're further packed and ensured that they're in pristine condition as they ship. Early on in fusion glass development, there were some manual steps, but we found that those manual steps could pose safety concerns. And so the robots were really developed to enhance our manufacturing process and to eliminate the safety involved in handling glass. We can create glass from extremely thin to 100 microns to 2 millimeters thick. Depending on the thickness of that glass, it really determines how many sheets of glass we pack in a crate. But crates in general can have hundreds of sheets within one crate. We really have limited range.
Once it's loaded into crates, the glass is then shipped off for finishing, which is done all over the world depending on the preference of the device manufacturer.
Gorilla glass is one of the toughest glasses out there. And what makes it tough is not only what you see here, because it actually hasn't obtained all of its strength at this point. After it's packed and shipped, it goes through a chemical strengthening process called an ion exchange process. The composition that we set up allows us to then take a finished sheet of glass, put it into a bath of hot salt, and in that bath of hot salt, sodium ions are exchanged for larger potassium ions in the glass. If you imagine those larger potassium ions packed into that glass, causing a much tighter and stronger compressive area on the glass.
So I think this is interesting. So this ion exchange technique, they produce this kind of glasses. So what we are going to propose new, just I will now discuss on that. You can stop the video here. Stop the video. Yeah. So this is basically glass ceramics. I will give just brief introduction. So what happens in glass ceramics, a polycrystalline solid prepares by controlled crystallization of glasses. So your starting material is glass, it's completely homogeneous glass, and we give some thermal treatment to give some kinetic energy to nucleation and crystallization. So by this process, some crystals, nuclei is formed and some crystals are generated, and we basically get this kind of glass, completely transparent, it converted to opaque glass ceramics. So depending on size of your crystals, it can be opaque, it can be translucent, it can be transparent. So if you can control the crystal size in nanometer scale, then you can make transparent glass ceramics, and which is much stronger than the glasses. So I will show you some examples. So there are some challenges. Basically, when you induce some crystals in the glass matrix, the transparency is going to be lost. So you have to control the crystal size precisely nanometer scale so that transparency is retained and it is useful for display applications. And mechanical properties also you have to maintain very high. So in order to achieve the transparency, you need to control the size of crystals, and also defect index matched between the glass phase and your crystal phase. If you can match it, then you can also have a very good transparency. Okay, and also for mechanical property, you need to have homogeneous distribution of nanocrystals, desired crystal phase, and surface strengthening. Also, ion exchange you can do with this kind of glass. Okay, so these are the things, molecular dynamic simulation and crystallization kinetic study, that actually helps in control crystallization. So how we do actually, if you have to ensure a large number of nuclei formed in the glass matrix. So if you have a large number of nuclei, then the crystals will grow in a very small size and uniform size distributed throughout the matrix. But if you have only fewer crystals like this, then your crystals will be much bigger and it will be dissimilar size and mechanical property will not be strong. So there is some technique so that you can ensure that large number of nuclei is formed. So we can do it basically through DSC studies. We can do some kind of analysis and we can basically determine experimentally the temperature for maximum nucleation. So that I am not going details into theory of that, but you can measure, you can determine the temperature for maximum nucleation and you can ensure large number of nuclei in the glass matrix. And also in our laboratory, we have done DSC and crystallization kinetic studies to basically determine the isothermal crystallization rate we can determine at different temperature. So for this glass, we see at 700 centigrade, there are around 300, 400 minutes you are having in your hand for complete crystallization. So you can control the rate of crystallization and control the crystal size. So those are the techniques crystallization kinetics helps you to control the crystallization size of the crystal that we are precisely doing in our laboratory in CGCRI. So these are the problems, and we mostly worked on spinel glass ceramics, magnesium and spinel glass ceramics. We have worked 5 minutes. Okay, done. So in case of ceramics also can be much stronger, but it is more costlier, and you cannot make large size for your TV display or any other big display. You cannot make ceramics. But ceramics is also having a transparency issue because of there are pores and impurities. That is actually missing in case of glass ceramics. There is no pore and no impurity, only small crystals are there. So that will be basically, as it is very small, you are going to have some kind of transparency that is useful for display applications. So I will just show you some examples that if you say this kind of composition, so base glass is having the fracture strength around 146 MPa. When it is made to glass ceramics, you are inducing some crystals, generating some crystals in the glass. The property is 251. There's a huge jump in mechanical property. And when this glass ceramics is again ion exchange, it is down to 487. So there is a multiple few order of magnitude increase in strength. That is possible with the glass ceramics, and that is again ion exchange. So you can, going in future, you are going to have some kind of glass which is really unbreakable and you cannot break it. So these are some examples I am just want to show that in case of glass, in case of glass ceramics, in case of glass ceramics ion exchange, there is a huge jump in mechanical property, right? So that is going to be the future of display material. So we have worked on magnesium aluminum plain glass ceramics, and there is quite transparent. If you see the soda-lime silicate glass, the property set of properties like hardness, Young's modulus, fracture toughness, there is a few orders of magnitude increment or enhancement of strength that we could see. And we have maintained this kind of, produced this glass ceramics with the highest level of transparency. You can see the transparency is around 85%, more than 85%. So this is more than enough for display applications. And how we are getting this kind of high level of transparency? Because we could control the crystal size. You can see it's a nanometer, so this is 20 nanometer bar, and you see it's a 15 to 20 nanometer. So this kind of precise control of crystal size we can do, and this is homogeneously distributed throughout the glass matrix. So that gives this kind of mechanical property, and that's basically going to change your future of display technologies. So we have also worked on lithium aluminum silicate glass ceramics, and we have started working on this, and we found that if you see that in case of glass, there is some property when it is made glass ceramics, the property is enhanced significantly, and we have not done the ion exchange yet, but we are expecting much stronger glass ceramics with the highest transparency, very good transparency. So this is my all I want to share. I acknowledge my colleagues here and SCRB and DRDO for their generous funding. Thank you all. If you have any questions, we can discuss. I'll be happy to have some questions from you. Yeah, please. How to get? Oh, we do with powder sample. We make it a very fine powder, less than 1 micron, and we do the transmission. We basically lay in a copper grid and
I know. Is before the processing or after the processing you are make the powder? Like you are heating at around 1800 degrees centigrade.
no, it is basically first we make the glass,
Okay.
then we give some heat treatment to create some crystals. So
Okay.
those glass ceramics we call. Then glass ceramics is grounded to powder. On that we are doing the tin.
That means you are ground this grass, then you make the powder and do the tea.
Yes, exactly. So I think there is no more question. Thank you so much for your attention.
So we are now on to the last talk. May we have Professor Narendra Bhojak, Department of Chemistry, Government Dongar College, Bikaner.
Hello. Green Plastic Innovative Concept Theory and Practice is the official title for my presentation. I convey my best regard to Professor GP Singh sir, Professor Akshay sir, and Dr. Manoj Shekhawat for providing this opportunity to me. I think I am audible. Backside, I am audible. Okay. Because at least for 10 to 15 minutes, you will have to concentrate on the board. I wish and I hope and I also assure you that if you concentrate for 10 to 15 minutes, I will be making less hurdle in between you and your lunch. This work is specifically designed for this conference because we are having one interdisciplinary research consortium at our institution, and Professor Mangal and Professor GP Singh are one of the pioneer for that from the physics department, and Dr. Manoj Shekhawat completed his PhD under similar topic. So for student point of view, I'll be concentrating on this aspect and little bit on this. If time permits, 2 to 3 minutes, I'll take advantage of this contribution of GCRC here. So be attentive little bit with this phrase that business is not for money, it's for solving the problems. Like one of the major problem which is being faced just now in this hall, I think that after lunch it may be solved, as I was discussing with the Professor Nagar. When we discuss about the challenges, these are the top 10 challenges in the world. In this particular presentation, I'll be concentrating only on the last 3, rather last 2, energy and health, which are more related with the physical chemistry, or rather should we say that condensed matter physics and condensed matter chemical sciences. Basically, it is a material science. But what are the solutions? So when I'm talking about the green chemistry or green chemical engineering, it is more inclined to provide the solution rather than emphasizing or creating the problem. One of the famous definition for green chemistry is that kindly do not raise any problem until unless you are not having at least one potential solution for that. So whatever we will be discussing in next 15 minutes with you, we will be having little bit potential and permanent solution for that. So when we are designing a problem, there are 4 thoughts where we should concentrate, particularly in the countries like developing countries like in India. We should concentrate on these 4 basic problems, where energy is nowadays one of the prominent problem which is related with the above 3, and also with the condensed matter physics and condensed matter chemistry. These are the top 10 areas. You must have heard recently within last week about the quantum dots. But our group is mainly working on these 2 things: targeted protein related problems or targeted augmented problems that we will be discussing. But in addition to these 10th, 11th is more interesting. 2 of our students are sitting here who are working on this. This is the impregnation theory. This is another theory, a novel theory on which Divya Shekhawat and Kanhaiya Lal is also working. However, they may not be knowing that what exactly they are doing it. But this has resulted us the filing process of 4th patent recently. Here what is happening, in the morning I was discussing about the in vivo problems of the dopamine and the impregnation on the polymer structures. So the solution is coming from here. So here the plasticity is also coming. Keeping the things simpler, I would like to give your kind attention here. आप सभी लेबोरेटरी के अंदर काम करते हैं. लेबोरेटरी के अंदर फिजिक्स, केमिस्ट्री, जियोलॉजी, बॉटनी, सभी की लैब्स के अंदर आप एसिड को थ्रोली बहुत आसानी से फेंक रहे होते हैं. जस्ट ट्राई टू फाइंड आउट द सॉल्यूशन फॉर वन क्वेश्चन. 1 मिलीलीटर स्ट्रॉन्ग एसिड जो LR ग्रेड का है आपकी लेबोरेटरी में, आप उसको सिंक में डाल देते हैं. हाउ मच वाटर इज रिक्वायर्ड फॉर कंप्लीट न्यूट्रलाइजेशन? This is question for all. How much water is required for complete neutralization without adding any other neutralizing agent? तो यहां से अपन शुरू करेंगे और जब ये स्लाइड दोबारा आएगी तो ये प्रेजेंटेशन एंड हो जाएगा. आपको देखना है कि इसका क्या आंसर हो सकता है. लेकिन ये क्वेश्चन बहुत इंटरेस्टिंग है और यहां से हमारा आज का प्रेजेंटेशन शुरू होता है. Which of the following is most hazardous? आप जस्ट गैस कर लीजिए. एज ए स्टूडेंट हैं तो मैं आपसे कहूंगा कि आप कहीं नोट करके रख लें, अदरवाइज आप इसको गैस कर लें कि विच ऑफ द फॉलोइंग इज मोस्ट हैजार्डस. बिकॉज आई एम टॉकिंग ऑन द प्लास्टिक, तो आंसर शुड हैव बीन द प्लास्टिक, बट आंसर इज नॉट द प्लास्टिक. नाउ मैंने पहले क्वेश्चन का आंसर आपको नहीं किया है, बाकी जो 3-4 क्वेश्चन आपके सामने रख रहा हूं उसके आंसर करूंगा. आंसर इज द सिगरेट. एंड व्हाई द सिगरेट? सिगरेट इज मोर हैजार्डस देन प्लास्टिक. यस. इंटरेस्टिंग क्या है, जो सिगरेट जितनी ज्यादा महंगी वो उतनी ज्यादा हैजार्डस. आप में से जो स्मोकर्स होंगे या जिनको पता होगा उनको मालूम होगा कि सिगरेट और बीड़ी में डिफरेंस क्या है. बीड़ी क्यों ज्यादा हैजार्डस मानी जाती थी? क्योंकि उसमें फिल्टर नहीं लगा है. सिगरेट में एक फिल्टर लगा हुआ है. वो जो फिल्टर है वो आपको निकोटीन से तो सेव कर रहा है, लेकिन वो उसको मोर हैजार्डस करता है. वो फिल्टर इस प्लास्टिक का है. तो वो फिल्टर की वजह से निकोटीन वेपर्स तो आपकी कम आ रही हैं, बट इट इटसेल्फ इज क्रिएटिंग इट्स प्रॉब्लम. अब प्लास्टिक की प्रॉब्लम क्या है आपने अभी एक बार आइडेंटिफाई किया, सिगरेट के साथ उसको क्लब किया. 5 मिनट बाद जब एक स्लाइड और आएगी, देन अगेन इट विल बी मोर इंटरेस्टिंग फॉर यू. तो आंसर इज सिगरेट. विच एयर इज मोस्ट पॉल्यूटेड? वापिस आप मन में आंसर सोचना है आपको 30 सेकेंड्स के लिए. तो आंसर इज योर किचन. इवन उसमें चिमनी भी लगी हुई है तो भी आपकी किचन मच मोर हैजार्डस है. बिकॉज आप मटेरियल साइंस की बात करते हैं तो नॉक्स प्रोड्यूस तो वहीं हो रही है. एंड इंटरेस्टिंगली इट इज क्रिएटिंग द नाइट्रस ऑक्साइड N2O, which is laughing gas, which was the major gas of World War I, and that is available in our kitchen, not at ITO Bridge of Delhi or at the other places. अब एक बार इस स्लाइड को देखिए, व्हाट यू इमेजिन, आई एम टॉकिंग टू ओनली स्टूडेंट्स, कैन यू इमेजिन नाउ? इफ नॉट, आई थिंक नाउ. So this is just the perception. How perception changes this way. जो आज मेजर ऑसिनिक प्रॉब्लम है, नेशनल इंस्टीट्यूट ऑफ ऑसिनोग्राफी गोवा की एक बहुत बड़ी स्टडीज है हमारे कोलैबोरेटर के साथ में वहां पर, उसमें ये है कि दिस इज क्रिएटिंग द बिगेस्ट प्रॉब्लम. लेकिन वो सिगरेट से बड़ी नहीं है, क्योंकि सिगरेट आपके फ्लश में भी जा रहा होता है. हमने प्रॉब्लम की बात की, और उससे 1 मिनट पहले हमने कहा था कि ग्रीन केमिस्ट्री की बात तभी करनी चाहिए व्हेन यू आर हैविंग ए पोटेंशियल सॉल्यूशन फॉर दैट. Until unless we are not having solution, we will not be discussing. So now come to the solution for 3-4 minutes, then again we will be discussing the problem, the major problem. जो हम टेक्नोलॉजी डेवलप करें वो इन 4 फैक्टर्स 5 फैक्टर्स पे होनी चाहिए. आई एम सिग्निफिकेंटली टॉकिंग अबाउट द 5th वन, दैट इज सेफ एंड सस्टेनेबल केमिकल, एंड दैट विल लीड टू द ग्रीन कैंपस. क्योंकि हम सारे एकेडमिक्स से हैं, तो हमें ग्रीन कैंपस और ग्रीन कैंपस के जो 20 कंपोनेंट्स हैं उनके बारे में डिटेल में पता होना चाहिए. वंस वी एस्टेब्लिश 20 कंपोनेंट्स ऑफ ग्रीन कैंपस, we will be leading towards the green auditing, and then we will able to solve the problems at least from our campus. कैंपस में खाली प्लास्टिक फ्री करने से प्रॉब्लम नहीं सॉल्व होगी. देयर आर 19 मोर कंपोनेंट्स which are related with the Cottle precipitator, flora, fauna, and 20 other things. Then sustainable lifestyle is there with related with the carbon credit. I am skipping it for the faster one because I want to come to the solution. This is the potential solution from where we can describe. And I think Professor GP Singh is sitting here. He must be, not must be, he is well aware of the facts that how these desert plants are more compilable or companion oriented towards the potential solution of these basic problems. Can you identify these two pictures? In one, I am there. I am just standing in front of the seashore of Bay of Bengal. And one is our collaborator, sir. He is from Bhabha Atomic Research Center. You may be knowing. So we were having one project at Pokhran. So they are from the Pokhran side, and I am from the, this is in front of Konark Temple. So identification is for this desert plant. अगर आप बीकानेर से जैसलमेर जाएंगे तो दोनों तरफ आपको दिखेगा, या बीकानेर से जयपुर जाएंगे तो भी दोनों तरफ दिखेगा कैलोट्रोपस प्रोसेरा, आक या आंकड़ा. आंकड़ा आपका पोखरण में डेजर्ट पे भी है, और आंकड़ा आपका बे ऑफ बंगाल पे भी अवेलेबल है. साइज का ही डिफरेंस है खाली. एंड दिस इज ऑल्सो एट दी हिली रीजन ऑफ राजस्थान. अरावली के रीजन में है, हिमालय में अवेलेबल नहीं है. इसकी स्पेसिफिसिटी क्या है? द फाइबर एक्सट्रैक्टेड फ्रॉम दिस is having very high tensile strength. Its extractability is important. That is a problem. We try to solve that, and we could able to inoculate its the profilable or profilable properties which is having the tensile strength. Now come to the problem of plastic. क्योंकि मैं 10 मिनट प्लास्टिक पे ही बात करूंगा, तो हमें प्लास्टिक की इंपॉर्टेंस और प्लास्टिक के हैजार्ड्स वो दोनों पता होने चाहिए. आई थिंक क्लियर फ्रॉम हियर, बट दिस इज द प्रॉब्लम. अब आप 3 या 4 मिनट के लिए सोचिए, यदि मैं आपसे ये कहूं कि प्लास्टिक की कोई मेजर प्रॉब्लम हाईलाइट कीजिए, तो पहली प्रॉब्लम क्या आएगी? दैट इज रिलेटेड विद द मैनेजमेंट, दैट इज विद द सोशल साइंटिस्ट पार्ट, कि गार्बेज मैनेजमेंट इज द बिग प्रॉब्लम, जो पिछली वाली स्लाइड में दिखा रखा था मैंने 3 स्लाइड पहले जो बताया था. दूसरी प्रॉब्लम क्या आएगी? बायोडिग्रेडेबिलिटी. प्लास्टिक की बेसिक प्रॉब्लम क्या है? बायोडिग्रेडेबिलिटी. लेकिन सोशल साइंटिस्ट की वजह से क्या थी? गार्बेज मैनेजमेंट. बायोलॉजिस्ट की वजह से क्या है? बायोडिग्रेडेबिलिटी. अगर हमारा प्लास्टिक बायोडिग्रेडेबल होता, क्योंकि ये नॉन बायोडिग्रेडेबल है, तो ना तो इसके नैनो पार्टिकल्स बनते, बायोडिग्रेडेबल होता तो, और ये ना ही ये प्रॉब्लम क्रिएट करता. लेकिन अगर आप फिजिक्स और केमिस्ट्री से हैं, तो आपके लिए ये दोनों प्रॉब्लम ही नहीं है. तो व्हाट इज द रियल प्रॉब्लम? अभी तक हम प्लास्टिक की रियल प्रॉब्लम पे नहीं आए हैं. अगर हम मटेरियल साइंस से प्रॉब्लम देखें प्रिपरेशन की, तो इसमें जो मटेरियल यूज हो रहा है वो है बिस्फिनोल ए. अभी जो आपने पानी की बोतल में से पानी यूज किया है, या जो आप अपने बच्चे को टिफिन बॉक्स में लंच देते हैं, या छोटे बच्चे को बॉटल्स के अंदर गर्म दूध दे रहे होते हैं, दैट प्लास्टिक प्रीवियसली कंटेनिंग बिस्फिनोल ए, BPA. आजकल जो प्लास्टिक आ रहा है उस पर लिखा हुआ है BPA फ्री प्लास्टिक. right? So bisphenol A was the problem because that was essentially to be added for the manufacturing of plastic related with plasticity. अभी एल्यूमिनियम नाइट्राइड की बात थी पिछले लेक्चर के अंदर, तो दैट एल्यूमिनियम नाइट्राइड इज क्यों रिमूव किया है, ये उसके हैजार्ड्स हैं. मैं सारे हाईलाइट नहीं करूंगा, मैं सिर्फ एक क्या यूज करता हूं, डीएनए मैथिलेशन. मतलब छोटे बच्चों को आपने बिस्फेनॉल ए वाले प्लास्टिक बॉटल में गर्म दूध दिया या गर्म पानी दिया, तो 50 डिग्री सेल्सियस पे वो आपके दूध में चला जाएगा. तो बीपीए आप उसको देकर के उसका डीएनए मैथिलेशन तो ऑलरेडी कर रहे हो. प्लास्टिक के हजार्ड्स जो सोशल साइंटिस्ट वाली थी, गार्बेज मैनेजमेंट या बायोडिग्रेडेबिलिटी, वो तो बाद में आएगी. आज आपके सामने पहले कौन सी आ रही है? पहले आपके पास में आ गई न्यूरोब्लास्टोमा, जो उसके साथ होना ही है. अब ये हुआ कि बीपीए फ्री जब डेवलप हो गया, तो बीपीए फ्री में कौन कौन से केमिकल्स हैं, ये एक लिस्ट है. इसमें सबसे लास्ट वाला यदि देखें तो पॉलीस्टायरीन है. पॉलीस्टायरीन इज ऑलरेडी ए पोटेंशियल कार्सिनोजेनिक. आपने बीपीए फ्री प्लास्टिक तो बनाया, लेकिन स्टायरीन तो डाल ही दी ना. और इंटरेस्टिंग है, चाय के जो कप पी रहे होते हैं, जितना शाइनिंग चाय का कप पेपर प्लेट वाला, उसमें उतना ही पॉलीस्टायरीन मटेरियल, और वो गर्म के अंदर तो जाएगा ही जाएगा. सॉरी मनोज जी, अपन दोनों यही करते हैं, मतलब चाय उसी में दे रहे होते हैं. इसमें एक और था डाईऑक्सिन, वो हमने छोड़ दिया, वो भी रिसेंटली यूज हो रहा है. बट अगेन इज दैट जस्ट ट्राई टू कंसंट्रेट ऑन 3 थिंग्स. हमने जो 3 पॉइंट आउट किए, सोशल साइंटिस्ट के लिए क्या था, गार्बेज मैनेजमेंट. बायोलॉजिस्ट या एनवायरमेंटलिस्ट के लिए क्या था, बायोडिग्रेडेबिलिटी. केमिस्ट के लिए क्या हो गया, जो एक कार्सिनोजेनिक है. बट इंटरेस्टिंग ये है, इफ यू आर रियल केमिस्ट, तो ये तीनों प्रॉब्लम ही नहीं. इन तीनों को तो अपने हटा सकते हैं इजीली, जो हमने किया. लेकिन चौथी जो प्रॉब्लम आएगी वो क्या है, वो देखिए. जितनी मैंने स्लाइड्स आपको शो की हैं सारी ओरिजिनल थी. इनमें से जो अब मैं स्लाइड शो करने वाला हूं, ये देखिए, आप कॉमनली यूज सॉल्वेंट्स आप हर जगह यूज करते हैं, अपने कंप्यूटर्स में यूज करते हैं, प्रिंटर्स में यूज करते हैं, हर जगह पर आप इनको यूज करते हैं. ये लिस्ट है उनकी, मतलब इसको मैं स्किप कर सकता हूं इस लिस्ट को. ये सारे कॉमन केमिकल्स हैं. इसमें एसीटोन और इथाइल अल्कोहल आपने बहुत सुना होगा. इथाइल अल्कोहल बहुत कॉमनली यूज केमिकल्स है, और एसीटोन भी उतना ही है. नाउ व्हाट आई एम गोइंग टू टेल यू, वी आर कमिंग ऑन द ग्रीन केमिकल इंजीनियरिंग पार्ट. ये एक स्लाइड है विच इज माई फेवरेट. ये क्या होता है इसके अंदर, दिस इज व्हाट आई एम गोइंग टू एक्सप्लेन यू. हम ये यूज करते हैं कि इंडस्ट्री अपने आप को इनैक्यूलेट करती है, कहती है कि हम हैजार्डस टॉक्सिक केमिकल्स यूज नहीं करते हैं, चाहे कोई भी इंडस्ट्री हो, प्लास्टिक इंडस्ट्री, फ्लेवर इंडस्ट्री, फूड इंडस्ट्री, पॉलीमर इंडस्ट्री, सेरेमिक इंडस्ट्री, ऑल अदर दे आर क्लेमिंग. वो क्या कहते हैं, हम तो इथाइल अल्कोहल यूज करते हैं. तो इथाइल अल्कोहल इज नॉट दैट वे हैजार्डस, क्योंकि ये तो आप बहुत सी जगह पर यूज भी करते हैं. बट द प्रॉब्लम इज दैट जब आपका ट्रेसेस ऑफ इथाइल अल्कोहल यहां से निकल रहा है, कोई भी इंडस्ट्री में से, आप लैब में भी कोई डिस्टिलेशन भी लगा रहे हैं, तो उसमें 70% सस्टेन होगा, 30% एटमॉस्फेयर में जाएगा. तो दैट 30% विच एवर इज गोइंग इन द एटमॉस्फेयर, क्लाउडिंग के साथ जब वापस आएगा, तो वो कहां पे आएगा, वो अंडरग्राउंड वाटर में जाएगा, सरफेस वाटर में जाएगा. यहां से प्रॉब्लम शुरू होती है. वो सरफेस वाटर या अंडरग्राउंड वाटर कहां पे जाता है, पीडब्ल्यूडी वाटर प्यूरिफिकेशन टैंक के अंदर. वहां पीडब्ल्यूडी वाटर प्यूरिफिकेशन टैंक में क्या होता है, हम क्लोरीन पास करते हैं, ब्लीचिंग पास करते हैं. वो क्या करेगा, हमने तो कहा था कि ट्रेसेस ऑफ सॉल्वेंट है, उससे कुछ नहीं होता. वो ट्रेसेस ऑफ सॉल्वेंट जब क्लोरीन के कांटेक्ट में आएगा, ब्लीचिंग पाउडर के कांटेक्ट में आएगा, तो नाउ यू रिमेंबर योर 12th क्लास केमिस्ट्री फेमस हेलोफॉर्म रिएक्शन. हेलोफॉर्म रिएक्शन में क्या होता है, एसीटोन और इथाइल अल्कोहल रिएक्ट विद इट एंड फर्स्ट कन्वर्ट इनटू मोनोक्लोरो एसिटल्डिहाइड, डाइक्लोरोएसिटल्डिहाइड, ट्राइक्लोरोएसिटल्डिहाइड, एंड फाइनली दिस कंपाउंड. इसको रिमूव कर दीजिए प्लीज. ये तो यहां पे क्लोरोफॉर्म आ गया. अब क्या हुआ कि जो इंडस्ट्री क्लेम कर रही थी कि वी आर यूजिंग द नॉन हैजार्डस इथाइल अल्कोहल, वी आर यूजिंग द नॉन हैजार्डस एसीटोन और इवन इथाइल एसीटेट, that has been converted into the chloroform, and by our default of chlorine, which was to be used as insecticide or purifying agent, now it has created the chloroform problem. The problem is that no RO, no water purifier even can identify and trace and detect. Removal is a far more distant thing. We cannot even identify and detect the amount of chloroform which is being actually spreaded by us. The problem is coming from here. Social scientist over, biodegradability over, chemist is over. The basic problem is striking now at the solvents. So we have identified this. After this, we designed that our problem is related with the solvent. So we started working on the solvent, and we were getting a lot of very good high intellectual collaboration from physics persons. जब मनोज जी वहां पे काम करते थे, जीपी सिंह साहब वहां पे काम करते थे, तो हम देखते थे कि जो हमारी प्रॉब्लम होती थी वो इनके लिए चुटकियों का काम था. जैसे मुझे ग्लास ट्रांजिशन टेम्परेचर समझ में नहीं आता था. अभी 1 मिनट बैठे हुए भी एमडी शर्मा साहब के साथ बात हो रही थी, तो उन्होंने एक और ट्रांजिशन टेम्परेचर पूछा, मैंने खाली स्पेकुलेट करके उसका आंसर किया. लेकिन जो आपकी प्रॉब्लम थी वो हमारे लिए बहुत इंटरेस्टिंग भी थी और बहुत आसान थी. तो दैट कॉम्बिनेशन अल्टीमेटली डेल्ट विद दिस, और इनकी इसके ऊपर जो हमने प्लास्टिसाइजर्स रिमूव करने का काम किया, दैट इज रिलेटेड विद द ग्रीन एक्सट्रैक्शन वर्क. एंड इंटरेस्टिंगली, in the morning when I was listening about one of the prominent lecture on the dopamine and the sulfide range electrical circuit preparation, I was thinking that if we could get some collaboration that we can remove it, that sulfonide, by using the simpler micellar system, so that not only will be utilizing for the vivo rectification, but it will also be for the submerging part of dopamine. So dopamine submerging is required, as well as you want to ask in between? Okay. Oh, then I'm not unhappy. This is not my problem. Voice is audible. Okay. They are asking to organize, not to me. नहीं, वो ये कह रही है कि भी वो.
Sir, I want to say that lecture is very informative and we are listening this thing, but due to this hot weather, we are not able to sit.
Okay, just 5 minutes more. Just bear with 5 minutes.
Otherwise,
Okay, 4 minutes.
On, then it would be beneficial.
Not more than 4.
Okay, then thank you, sir.
Because from here, actually, I'll be going to start the technical part, and most of the persons are not interested in technical part. I think Professor Sarkar must be knowing. So from here, actually, we start. But I will like to add here, when we establish the fact of the using of micellar systems, particularly reverse micelle, and I remember the thesis of Dr. Balwinder Singh, who is in Germany now, in France now. He was with you, Manoj. And in that case, we got the problem of toxicity of surfactant. Surfactants are fine, but if there is toxicity, these are useless. The same problem with you. But again, the solution is coming from desert plants. The same Calotropis procera and the plants like Rathi are providing us the biosurfactants. We use the biosurfactant here, which are having the almost negligible type of toxicity. Negligible, no, is zero toxicity. So what we could able to do, we could able to get the different type of the surfactants, more than 30 surfactants we tried, including the biodetergents and biosurfactants, and we could able to get the reverse micelles. Now, why the reverse micelle? Because our main motive was to extract the lignocellulonic material or cellulolignic material from the Calotropis procera. So what was actually happening? The rod shape micelles first, and then we went for the reverse micelle. So why rod shape? I can explain in the next slide. That these are providing us two types of importance. One, they are exhibiting on the micellar core. So there is interesting increase in the absorbance because they are sitting on the micellar core. So interesting increase in the micellar core. So absorbance increase is also there. And that in absorbance increase is providing us the bioluminescence. And that is useful for making different kinds of probes. But it is also stabilizing. That stabilization, particularly above CMC, is restricting us to stop the system, and then we can extract the material. Extract the material, And that material is very specific. And from here, the nano extraction starts. We are having two compounds, isoflavonoids and flavonoid. From one particular, I can extract the flavonoid. From other particular micellar system, I can extract the isoflavonoids. You can find the structural difference here, and this is why we got the isoflavonoid release, and we got very good publication because of this. And from here, I can almost summarize it. Here you can find this one. This extraction is due to the approximately 100 CMC biosurfactant, and that was coming in the fibrous material. And that was very important for making the, this is the mechanism which we could able to publish, and you can visualize that this is the extraction part. So once we get the extracted material from there in the form of nano composite, nano fiber, we can go for these many steps. I think all persons are knowing about this, and these are the different properties. We also went for the several studies. इन सबको मैं skip कर रहा हूँ because ये अपने आप में 1-1.5 घंटा ले सकता है. तो what we did, we got the composite material from that technique, that which I discussed with the green extraction technique, and we also could able to file one particular patent on that. And we got 28% to 32%, 28% to 32% biodegradable material, जो आज हमारी लैब में हमारे पास easily available है, that is 32 to 36% biodegradable plastic. Yes, sir. I'll complete. So this is from the Calotropis procera, arc or akada, which is coming from the wasteland desert sites. Just using that technique, which is avoiding the social scientists, using the biodegradability, we are not using any chemical, we are using the biosurfactants, and then we are using the micellar system, so extractable materials are there. Now, interesting part is that why I named 2 students from our lab. We want that they should design for this, and recently you must have heard that now the food wastage is more recurring than the wastage of the detergents, wastage of the plates. This is why we can design using the Calotropis like materials. Professor GP Singh worked on the care. Now in the next step, plates बन रही हैं सर care की. केयर की आपने प्लेट्स बनाई या ईडेबल मटेरियल की प्लेट्स बनाई, या कोन्स तो आपने सुना ही होगा, कोन्स में आपने आइसक्रीम डाली और कोन्स को आपने साथ खा लिया. अभी अगर अपन लंच करेंगे और उसमें प्लेट्स हम साथ ही खा रहे हैं डेजर्ट की जगह पर, एंड दैट इज अवेलेबल. Though it is expensive, it is tedious to prepare, but available in India itself. I hope and wish that by the next conference, क्योंकि आप 2 या 4 साल में करवाते हैं, तो बीकानेर के अंदर भी वो अवेलेबल हो जाए, और एटलीस्ट वो नहीं तो हम समोसे तो प्लेट के ऊपर रख के खाएं, जो प्लेट भी हम साथ में खा लें. तो दिस इज द इंटरेस्टिंग पॉइंट. ड्रिंक, पानी की बोतल आप यहाँ छोड़ के जा रहे हैं, वो प्रॉब्लम है. जो एनकैप्सुलेशन है वही साथ ले लिया जाए और उसी को पी लें. वो स्वीट्स का काम करेगा, मिठाई का, और पानी मिल ही रहा है. कैरी, ये एनआईओ के साथ एक कोलैबोरेशन है नेशनल इंस्टीट्यूट ऑफ इम्यूनोलॉजी में. ये जो टर्टाइल्स हैं, इनके लिए प्लास्टिक सी पोल्यूशन बहुत बड़ी प्रॉब्लम है. लेकिन अगर हम फेंक ही ऐसे वाले रहे होंगे जो टर्टाइल के लिए फीडिंग मटेरियल है, देन इज फैंटास्टिक. So he will say that please let me eat. At the end of time, I am just telling you that how much water is required. Sir, this answer is 20,000 liters for 1 milliliter strong acid. 20,000 liters. And I am happy to tell you that in our institution we could able to design. This is the simple calculation anyone can do. लेकिन condition क्या थी? कोई भी neutralizing agent डालना नहीं है. डालने के बाद तो कम करेंगे ही ना, right? So we could able to establish one neutralization center in our institution, and almost 3-4 persons are sitting here who were involved there. इसके अलावा बहुत सारी चीजें हैं सोलर की, मैं इसको स्किप करना चाहता हूँ. तो आई कैन कंक्लूड दिस. This was the green sanitizer. It was the another patent on which we were working. And I think here you can find another MD Sharma ji is there, Nagar Sahab is there. This is the use of plastic in a different way. Condensed matter is not our research area. Our research area is green chemistry. Now we have turned into the smart science laboratory, augmented and virtual reality, due to the consistent help of Professor GP Singh and Professor Mangal Sahab. You can find that both of the ministers are there. We are also working on the green printing, 3D printing. इसमें polylactic acid use होता है, जो polylactic acid can be replaced with the Saji based material. This material is available on the website. Here I would like to end it. I started my work, this green chemistry work, with Professor John C. Warner.
1 minute.
Yes, sir. He is the president of Warner Webcom Institute. Then we are having one collaborator from Dockless Biotech, and finally we are having these many facilities. If you want to collaborate with us, we are having the Bikaner Interdisciplinary Research Consortium. Last but not the least, I would like to definitely convey my best regards to all of my mentors, particularly BC Das, who is now at Harvard Medical College and providing us almost all facilities free of cost, and the students who has really worked on this. Thank you all. This is one of the very good research paper we have recently published with the elsewhere. Thank you.
Just wanted to know why you have chosen two different areas for your plants. So the Pokhran is a very...
Yes. This is an interesting question, and I hope that one should ask this, and thank you very much, sir. Pokhran we selected because we were having the Bhabha Atomic Research Center project. They gave us the project, so that was essential. कोणार्क टेम्पल जो आपका वहां पे है, वो सेलेक्ट इसलिए करना पड़ा क्योंकि मेरी वाइफ को हर टेम्पल पे जाने का शौक है. तो वो टेम्पल पे जा रही थी, कोणार्क टेम्पल पे, मैं शीशोर पे बैठा था. तो आई फाउंड दैट दिस इज, so that was incidentally. So that correlation was very interesting. And after that we have visited to more than 100 temples. जो नीचे एक स्लाइड थी वो भी एक, अगर आपने सुना हो तो, रणकपुर का टेम्पल है. राजस्थान में कभी आप विजिट करें, उदयपुर के पास में. रणकपुर का टेम्पल किस लिए फेमस है, बच्चों से पूछ रहा हूँ. अगर कोई उदयपुर से आए हो तो रणकपुर का फेमस है किसके लिए? जैन टेम्पल्स के लिए. लेकिन जो हमने शो किया था वो जैन टेम्पल नहीं था, वो सन टेम्पल था, और वो बहुत बड़ा था. So that was very interesting. So this is really interesting.
Please. बहुत बहुत धन्यवाद डॉक्टर नरेंद्र जी भोजक फॉर योर फैंटास्टिक टॉक. मेरी एक सिंपल क्वेरी ये है कि जो आपने ग्रीन प्लास्टिक बनाया है वो बहुत उम्दा चीज़ है, लेकिन मेरे दो छोटे छोटे सवाल है. 1 किलो ऐसा ग्रीन प्लास्टिक बनाने के लिए कितने आग की जरूरत पड़ी? नंबर 1. कल को मान लीजिए इंडस्ट्रियल लेवल पे इसका प्रोडक्शन होता है, तो क्या आग की जो मात्रा हम क्या मतलब जितनी ह्यूमन को चाहिए वो फुलफिल कर पाएंगे? और अगर आग बहुत ज़्यादा कटते हैं तो इसका कोई दूरगामी प्रभाव जलवायु पे या इस पे होगा क्या? ये थोड़ा आप बताइए. थैंक यू.
सर अगेन इट्स ए वेरी इंटरेस्टिंग क्वेश्चन एंड वन मस्ट आंसर इट. अभी ये सर 32 से 36% बायोडिग्रेडेबल है. इतना स्टॉक हमारे पास अवेलेबल है जो कैलोट्रोपस प्रोसेरा से हम इजीली निकाल सकते हैं. लेकिन इसके अलावा हमारे उस प्रोजेक्ट में जो बीआरसी सैंक्शन था, 12 डेजर्ट प्लांट्स आल्सो आइडेंटिफाई, मोर देन 12. उन 12 के 12 पे काम ऑलरेडी वर्किंग स्टेट पे है. बट प्रॉब्लम इज दैट जब हम कमर्शलाइजेशन पे जाते हैं और किसी इंडस्ट्री से बात करते हैं तो उनका पहला क्वेश्चन होता है गो फॉर द 50%, एटलीस्ट 50% बायोडिग्रेडेबिलिटी. अगर 50% बायोडिग्रेडेबल हमारा बन चुका होता तो आज मैं शायद यहाँ नहीं होता. Once we get the 50%, although at this moment we have scored more than 44%, that I am just disclosing you because of our college affinity. But once we get the 50%, almost all industries are ready to take it. लेकिन आप ये समझिए कि जिसने जो स्टार्टअप बनाया इसका ईडेबल प्लास्टिक का, that is 100%. So we can lead towards that. That should be restricted with the plasticizer's ability. अब आप एक चीज ये कह सकते हैं कि 50% कब तक होगा, तो डूंगर कॉलेज का फिजिक्स डिपार्टमेंट जब पूरी तरह से साथ होगा तो 50% हो जाएगा।
अरे भाई, अभी एक बात सुनिए, आपको जवाब नहीं देना है, प्लीज। नो, यू आर नॉट टू रिप्लाई। ये रख दीजिए। Enough of replies. I want to make a statement, which is, I think the plastic problem of pollution of plastic, yeah, it is not against you. I'm general talking. It has come because of affordability, because of prosperity. Let me tell you, I came to Mumbai in 1965. Bombay Municipal Corporation, anybody entering any restaurant demanding water, you have to give, you can't say no, because they were not providing general water supply to most people on the road. So if a hand cart puller, physical labor, I have seen them entering any Irani restaurant or any which they won't go to 5-star hotel. It is not convenient, but they have to stop their work and give him water. अब धीरे 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 क्या होगा, लोगों ने मांगना भी बंद कर दिया और देना भी बंद कर दिया. Let me tell you, India has a history of this piyau business. In Bombay, even now the old piyaus are still there, जहां आप पी सकते हो और लोग पिलाते हैं. And Indian business community had installed in Hyde Park, London, donated a piyau to tell the British people this is possible to solve. अभी भी वो है वहां पर, but who cares? We have money. I'll tell you, every day we throw so many things. Now I was in my hometown in Punjab. एक मिनट और देना. एक नया चीज चली है, फैशन चलता है, लाहौरी जीरा. Punjabis, they gave me Lahori jeera. It comes for 10 rupees. Drink and throw. उनको टेस्ट अच्छा लगता है. You are corrupting and getting corrupted back. So ये हो रहा है. But होता क्या है? You can still restrict. I give you my example. यहाँ तो मैं पी रहा हूँ. मैं हर रोज जब सुबह सैर करने जाता हूँ, मेरे हाथ में वो ही सेम प्लास्टिक बॉटल लास्ट 6 months से है. वाई? मैं घर से पानी भर के लाता हूँ, 200 cc है. पानी खत्म हो जाता है, तो रास्ते में कूलर है ना हमारी कॉलोनी में, वहां से आप पानी भर लो. आर यू अशेम्ड टू फिल वाटर फ्रॉम द सेम कूलर? वो पानी अच्छा है ना? नो, एवरीबॉडी नीड्स another bottle, one more bottle for Italy. Sorry, thank you.
Thinking. We are leaving that. Thank you, sir.
You are right, but I think हम लोग बीमारी को इलाज ढूंढते रहते हैं सारा टाइम. Thank you.
Thank you, sir. Thank you for this wonderful session of invited talks that we had here. Before announcing, I would like to just inform you that some person has lost his phone. This is Samsung 32 phone. Any person who has lost this, kindly come and collect it with it is with Dr. Manoj Singh Shekhawat, sir. So kindly inform any person who has lost his phone. Now, may I request Professor J.V. Yakmi sir and G.P. Singh sir to kindly hand over the mementos to the person who have given the invited talks, to the professor who have given the invited talk. First of all, I would like to invite Professor Vivek Kumar Gupta sir. Professor Vivek Kumar Gupta sir.
सब एडवांस
Now may I invite Professor Sampat Kumar Vishwas sir. May I request Dr. Atayr Rahman Molla sir to kindly come on the dais. I request Professor Narendra Bhojak sir. Now I request Dr. Smita Sharma ma'am to kindly come on the dais and give the memento to JV Yakni sir. Memento for this acting as a chairman for the session. Now I request Dr. Ajay Nagar sir, Dr. Ajay Nagar sir, to kindly give the memento to Professor GP Singh sir.
नहीं यार से ये 1 1 से सेशन स्टार्ट होगा हां से नीचे नहीं लगती ये पीछे तो लगा हुआ ये से
Thank you, sir. Thank you very much for this wonderful session that we have been the audience for such a wonderful session. Now it's time for the lunch session, which is an important session apart from this. So we will go for the lunch and then assemble for the oral sessions and the poster sessions. So now the session is off for the lunch session. Thank you. The